We're ready to start initializing the hardware. We've done a little bit of hardware initialization up to this point, and that was the cache memory. And the reason that that had to be done first is unless you have a stack, you can't use C code. So maybe think of it this way is all the stuff we did in parts 1 and 2 and 3 was just to get the C code started. And then in part 4, we started to get into the C code initialization, which went back and did some of the memory type range registers. So we haven't done a whole lot. We've just got this CPU block. Now, in the past, the CPU interfaced directly to the memory and directly to the I/O, meaning you just had an IC chip that was a CPU and then some pins on it, and the pins went directly to the memory or they went directly to the I/O, and that was it. No longer. No longer. The CPU is off on its own area and it communicates through these other hardware devices. What are we looking at? What are we looking at? Well, here's this little square called a CPU, and then this thing called a front side bus, and a clock generator. Somehow the G was chopped off there, but there's a clock generator for the CPU. In other words, when you have a CPU with a certain speed, like 1.8 gigahertz or something like that, that'd be the clock going in there with that. Then there's this north bridge, and that's called a memory controller hub. Then the south bridge, which is the I/O controller hub. And then the various different things coming off here. CMOS memory. Okay, we talked about CMOS memory a little bit earlier. Here's an audio codec, Ethernet. Wow, what's all this stuff on there? USB. These are a couple hard drive interfaces. This is the PCI slots. We'll talk more about that later. High-speed graphics bus, Super I/O. Way down here is, way down here is the flash ROM BIOS, which is what we started with on all this. Now, what's interesting is this is close to the AMD, but this was chipset layout from the Pentium 2, Pentium 3 era. So this chipset was separate from the Pentium chip. Now we're talking about a system on a chip, and all of this stuff is included except for the, serial port, LPC. Okay, this is low pin count bus down here. And let's see what else we got here. Notice here's the memory slots. Those are separated from the CPU. Let's get deeper. Now we talk about the fact that inside that CPU block, there's actually different cores. Now the Stony Brook, which is what not the Stony Brook, the Stony Ridge processor that we're talking about has 2 cores, so this matches up very well with that. Notice the L1 cache here. The core communicates directly with the L1, so that's the high speed. You notice there's nothing in between there. You've got the CPU core. So let's imagine that we're executing an instruction. We have a bunch of instructions in the cache, so we're executing the cache directly. And the same thing is true here. So they've got their own area where they're executing stuff and taking care of data back and forth. Then there's something called the backside bus, and this is internal inside that CPU block. Then we have the bus interface and L2 caches. Now notice that both of these lead into this area, so we have shared memory between these two. So if this core wants to communicate somehow to this core, then we can do it through this memory interface right here. As we move down in this diagram, notice the front side bus. So this is the front side bus that went and communicated with those controller hubs and so on. Now let's go back to boot block. Boot block is what this whole thing is about. Boot block is all running out of the double EEPROM SPI chip. Here's boot block start and boot block end. So what we have to do is figure out what goes on in all of this stuff. And what we're going to focus on right now is boot block SOC early init. And SOC early init is defined in this other boot block file. And let's bring that to the top so we can look at it. SOC early init, and that is defined, has two things in it. Boot block FCH, and that FCH stands for Firmware Controller Hub. That Firmware Controller Hub is the device that ties into that front side bus that we just talked about. So we need to find out where this thing is defined. And it is defined in this file, early firmware controller hub. And here it is, boot block firmware controller hub, early init. And this is, let's see what happens here. Reboot equals 0. So that is used up here to say if reboot warm reset. So since we're not doing a reboot here, that warm reset, we won't have to follow down that track. Let's see if there's any other things we have to look at. Well, let's see. There's a lot of things that happen. So this is what we want to deal with. So we're going to have to find out where each one of these categories is defined. So there's quite a few little functions here in this one. So remember, this is just the first step. And it's interesting to say that this is inside the AMD firmware that establishes that system on a chip. So we're all inside that system on a chip. That's what I was trying to say, and I couldn't get it out. Here's the first function. And this ACPI MMIO, if we look up the acronyms in Core Boot, we see that the ACPI is the Advanced Configuration and Power Interface for letting the OS control power management. So that gives us a little idea what's going on. So if we examine what goes on here, there's a 32-bit variable here. The variable is loaded with a PMIO read 32. So it reads from this port number. Notice it's a decode register. And once we read it in, we OR it with this enable, which that's what it says, enable the decode. So we enable that one bit, and then we write it right back. Well, that was easy. Let's see what's next. What's next is, low pin count, enable ROM. Low pin count, enable ROM. So let's find a nice little file that'll tell us about that. Here's low pin count, enable ROM. And let's see what happens here. Let's look at this comment here. I think this will straighten things out for us really well. Enable 4 megabytes of LPC ROM access. And that 4 megabytes, if we count up these addresses here, notice this is the very end of ROM. And let's see if that ends up being 4 megabytes. Let's see, 1, 2, 3, 4, 5. Yeah, I think that's going to be 4 megabytes. That seems to match up pretty well because 5 would be the 1 megabyte range. So we got C, D, E, F. That'd give us 4 megabytes. We got through LPC enable ROM. Now we have LPC early init. Let's see what early init does. Enable controller, disable decodes, set SPI base address. So that's the SPI base address. Who knows what that value is, but I think that sets things up for the SPI ROM. Next choice, LPC enable port 80. Whether I mentioned it or not, port 80 was used for the post codes so that you could do some debugging. So let's see exactly what the details of that are. Here's LPC enable port 80. We're doing some PCI and PCI write config. I think we can get port 80 on the PCI bus, which is that acronym. I don't come up with the exact results right now. Next, SB. I wonder what SB LPC decode means. That one's actually covered in this file. And if we go up far enough, we'll find it. Here's SB LPC decode. Here's temp. Temp is a 32-bit variable, and this builds up all the different values in that 32 bits. And let's see what else happens. And then the final thing is LPC enable decode. So the LPC enable decode takes all those values up here and causes those to occur. Next, we've got the Firmware Controller Hub SPI early init. So there should be a SPI file that we can help us out with that. The SPI early init. Okay, enable SPI ROM. I think we saw that function in the LPC utilities. Enable SPI prefetch, SPI configure, and another SPI configure modes. So it's setting things up for the SPI bus, which is where the ROM is. And we've been using the ROM already, but this makes sure that everything works correctly. Next on our list is defined in SM bus speed. We need to find out what the SM bus is. The SM bus is a system management bus. That's where those letters come from. And we set up the speed of the bus. And whatever that SM bus is, we set everything up correctly with that. Next on our list is Firmware Controller Hub enable this CF9IO. So some special IO that we want to deal with. Starting to get the idea of some of these details for this firmware controller hub. I'm not going to go any more through this. I want to mention this enable AOAC devices. This AOAC is always on, always clear. Set up the UART and disable keyboard reset. That pretty well completes the idea of the SoC early init. It's all about that firmware controller hub. Back in boot block. Remember back in here, boot block start, boot block end. I think we're getting kind of close to what's going on here. Boot block main board init, main board early init. Now, main board init doesn't have anything. For the Bilby AMD board that I chose, there's nothing to do. However, early init, there is something to do. So let's see what's going on with that. Here's early init. And let's see what we do. Program early GPIOs. Okay. So GPIOs are configurable, meaning that you can change them to either, the pins can either be input, output, or various configurations. I'm going to just make this less painful and go back to the boot block. Right here. And we're going to do some things with CMOS unless I want to create a video just on CMOS. And console init. Console init is that one's kind of interesting. We turn on the print K feature and some things like that so that you can actually see stuff on the console. Let's see what else is now. Here we run the ROM stage. Console init is almost a video in itself. SoC init, that's not so interesting. We can easily pull that one up. Let's see. SoC init gives us boot block firmware controller hub init, reset the I2C peripherals, set the power failure state, as the I2C bus is set up, and some other stuff like that. So that is where I'm ending up. Have we lost our place? Maybe just a little bit. So if I'm going to do the console init, that's going to be a separate one. I hope you got the general idea of the firmware controller hub initialization and how it plays a part in getting the whole system started up.